Hi guys, my name is Raj Singh. I'm a staff SRE and architect at Box. In today's session, I'm going to be talking about Kubernetes observability and best practices that we follow at Box. So quick run through about the agenda. We're going to talk about Box, who we are, Kubernetes at Box, observability at Box, how we do Kubernetes observability at Box, and troubleshooting. Box is the content cloud, a single platform that empowers organizations to manage the entire content lifecycle, work securely from anywhere, and integrate across best of the breed apps. It's founded back in 2005, is trusted by 69% of the Fortune 500, including a wide variety of industry verticals like AstraZeneca, General Electric, JLL, Nationwide, headquartered at Redwood City, have offices across the US, Europe, and Asia. And for more details, please visit box.com. And as you can imagine, we deal with data and lots of them come in and out on a daily basis. And so we have to support it with our platform. So we've adopted Kubernetes back in July 2015 when it became GA for the first time. As we developed, learned more about Kubernetes, we started adopting services onto it. So back in 2016, we made it GA with the code name Skynet. In 2017, 8% of services and close to 150 nodes were running Kubernetes. In 2018, this grew to 20% of the services and 850 nodes representing 10% of the data center. And in 2018, we got 50% of services, about 24% of the data center. And currently, we host about 200 services, representing 85% of Box's stateless footprint, currently running Kubernetes 119 across all of our clusters. Close to 3,200 nodes with 600 in the largest cluster, 35% of Box's data center footprint. We have 10 prod-grade clusters across 3 regions with 30K pods and 9K in the largest cluster. We have also adopted at the same time around this period GKE in the public cloud. We're running 12 GKE clusters and also adopted stateful sets. So as you can see, during this journey, we had to deal with the complexities of Kubernetes, and we had to leverage the tooling that was available at that time and iterate on it to make it mature so that we can run our services fast and secure. Kubernetes at Box over the hood. Each cluster on-prem, we make sure that the control plane is scalable by having separate events etcd. Over the period, we identified etcd being one of the core components and a deciding factor which determines the number of nodes that we can have in a cluster. So we ended up having a separate etcd and a regular etcd with SSDs. And these get patched on a daily basis. We have a automated patching framework, which customized checks for pre and post maintenance so that we ensure that the cluster is always healthy, even when the maintenance is going on. We also have a control plane, which is scalable by itself independently. The control plane nodes consist of the Kubernetes API server, scheduler, control manager, etc. All of these nodes are grouped together using Anycast, leveraging BGP to provide HA. We run a BGP client on each of those nodes, which poll the API health on a regular basis and advertise and withdraw the routes into the BGP accordingly. And we place these control plane nodes strategically so that the traffic is well balanced coming in from all of the data plane. On the control plane integrations, we have few services that we provide for all of our user applications in the form of sidecars. We have PKI infrastructure, which is our Box internal CA, which gets added as a sidecar for services requiring certs, and it gets rotated automatically. On the secrets, we have HashiCorp Vault, open source on the on-prem side. We have a sidecar that allows the services to be able to interact with Vault and refresh secrets. On the network policies, IPAM for pod networking and policy federation, we leverage Calico. On the service discovery side, we have Smart Stack, which provides client-side load balancing. There's no ingress controller here. The client-side load balancing allows each pod to discover and load balance traffic both north-south and east-west within the cluster and across the Kubernetes clusters. We are also leveraging Istio. We are working towards moving into Istio as one of our roadmaps. On the image management, we leverage Artifactory. We also have a Artifactory cache set up on-prem to reduce the speed of downloads and costs by reducing the need for pulling from the upstream. On the pipelines, we leverage Jenkins. Multi-tenancy is set up using Kubernetes namespaces and RBAC policies. And the image on the right side shows the full mesh setup that we have for Calico and SmartStack between the clusters within on-prem and between on-prem and public cloud across various regions. Observability at Box is a layered approach. It's not just providing metrics, logs, and traces, but to enable SRE teams with visibility to the customer experience, proactive anomaly detection and mitigation in order to reduce the mean time to detect and recovery. Each box on the right-hand side represents a observability domain in itself, where we define what to collect, how to collect, alerts and dashboards, etc. And you can see the different layers in here. Kubernetes itself is one of the layers. All of these layers combined provides us the visibility that we need to be able to serve our customers. As we are a hybrid cloud, we wanted to have a unified approach to observability, which is cloud agnostic. We have a rich and flexible unified tagging model across the clouds. We tried to use the same model between on-prem and public clouds by using the same set of pipeline tools that collect and export metrics. This allowed us to have something called as dynamic DR visibility, where we can quickly, easily move traffic and workloads between on-prem and public cloud while not losing any visibility. We believe that observability has to begin from the code. The metrics and logs gets exported from build and deploy, and also from the platform and services standpoint. This is our observability flow. On the bottom, you see the logs getting collected on-prem using Splunk Forwarder, which provides custom filtering and enrichment. On the public cloud side, we either use FlowND as necessary, and all the logs gets collected into a custom PubSub. From there, gets extracted and filtered and enriched and sent to Splunk, where we have defined alerts and charts, which then is integrated into PagerDuty and Slack. On the on-prem side, we collect the hardware and host level components, things like the disk and memory components, the system services, certs, API endpoints, network, etc., gets collected from agents like Sensu, that sends to Sensu UI, and tCollector that sends to Wavefront. And NPD, which is a node problem detector, is an upstream open source tool and that collects metrics which are relevant for Kubernetes. All this gets aggregated into Wavefront. Sensu is primarily used for on-off kind of checking to check the health of various components. On the control plane side, we have, again, Sensu and Prometheus collectors, which gets added as a sidecar. We collect all the components that come right out of the box from Kubernetes pods, the API server scheduler, HCD, etc. We also run some integration tests and collect metrics periodically, data plane capacity and patching activity, etc. On the deployments and daemon sets, we leverage kubestate metrics, which is an open source tool that has been developed at Box and has been open sourced some time ago. We leverage all of the metrics coming in from various components of Kubernetes and get sent to Wavefront, along with the other collectors like Prometheus and NPD. All of that gets integrated, aggregated into PagerDuty and Slack. On the observability for Kubernetes, now that we have all the metrics, logs, and traces, we wanted to identify how to tie all of these data into defining our SLA, SLO, and SLI. So we took a customer-based approach where we tried to define what customers care the most. By taking this top-down approach to identify and build metrics, it allowed us to reduce noise from signals. And during that exercise, we found 4 key areas that define customer experience. The first one is deployability. This ensures that the workloads of the services are deployed within SLA, regardless of their size, their scale, region, single region or multi-region, public or private clouds. This also includes the time it takes to onboard a service, configure them, and get deployed through our CI/CD pipeline. And then we have availability. Here we define something called as a critical replica availability, which I'm going to talk about in a minute. This defines the uptime of the services while accounting for all the maintenances. And then we have serviceability, which ensures that the services are able to serve 100% of peak traffic at all times to be able to run services securely and in an automated fashion. On the service availability side, we've defined what's called a critical replica availability. The way it works is the customer defines critical replica thresholds, which is the minimum healthy replicas that defines the availability of a service. Based on that, we auto-configure Kubernetes protections to serve those critical replicas. Like we define the PDBs, readiness and liveness probes, the max surge for updates, and this gets calculated as the replica overhead for protections, which is a buffer of additional replicas that are needed for the service. As an example, we measure here the cluster group defines the Kubernetes clusters we have per region, and the critical replica availability percentage defines the SLA for that group of clusters. For Kubernetes observability, for each service, we take a policy-driven approach, which allows us the separation of concerns, where service owners define their signals and thresholds, platform owners define our platform signals, SREs define the policies and standards, and this allows us to set up monitoring just as an abstraction. On the right-hand side in the figure, we see how we define the infrastructure components using libsonnet, which is a abstraction on top of using JSONnet. Components like Envoy and Skynet gets defined there, and the service configuration leverages those signals, and we get the service info along with it. All of that gets merged and consumed by a policy-driven observability and abstraction layer that provides the functional abstractions or leveraging predefined charts and alerts. The outcome is that we get the alerts and dashboards in a configurable in JSON format. The policies define our health definitions in 6 golden rules in what we call as latest, which stands for latency, availability, throughput, error rates, saturation, and traffic. It also provides a scope, whether it's canary, non-canary, environment, and region. It provides a standard set of dashboards and predefined chart formats. The outcome of all of this is that by having all services follow the standard, we get a single pane of glass, what we call as all services observability dashboards, which is a dashboard with literally all the services that we use at Box. And each of the component in that pane provides drill down capabilities while providing visibility into the dependency mapping of all the layers like infra, platform, and services. All this provides us a standardized and programmable way of defining the charts and dashboards and alerts. As I mentioned earlier, by using a declarative signals and dashboards, the services get common signals out of the box. The signals and dashboards are coded alongside rest of the application configs. We define common patterns, libraries, flexible threshold definitions, all of which are configured as code. For example, signals are defined such as container CPU, which provides CPU metrics and charts, container restarts, service replica count, etc. All of these are functional definitions. And we have immutable dashboard definitions per service with functions such as like create dashboard, create dropdown entry, and more. As an example, you see one of the service here where it's showing the CPU metrics and CPU usage. By leveraging immutable dashboards, we see a consistent view for all the services. All of these dashboards gets consolidated into a single pane, and this is a snippet for Kubernetes components from that pane, which shows the overall health of the Kubernetes clusters. It has the ability to drill down. So if you click on one of these panes, it drills down to further details. For example, here is showing the clear server errors, latency, etc. for all the Kubernetes clusters aggregated. Further drill down, it will show all the alerts that have been fired for a given component within a certain time and environment. For example, here it's showing the Kubernetes API server dashboards. Now, besides that, we have a set of tools that proactively take actions to remediate issues. We have an API server sidecar, which is called Kube API Server Monitor. It watches for 500 errors of verbs and fails the liveness probes if a threshold is reached. As a result, it bounces the API server. And then we have a service called Kube IP Tables Tailor, which watches for IP table logs for drops and updates the corresponding pod events. This allows quick visibility into network policy issues, and this has been open sourced. We have an automated testing framework that runs automated tests on all Kubernetes components. For deep inspection, components are defined as plugins, and checks are dynamically configured. We have a service called Kube Node Remediator, which is a distributed service, runs per cluster, watches for NPD conditions for all the nodes, and triggers Ansible plays to remediate them automatically. We've recently open sourced Kube Exec Controller, which watches for pods which were execed using kubectl. This is to comply with our security and compliance. All of this has allowed us to troubleshoot services on Kubernetes platform. The diagram shows a typical flow that we use for troubleshooting. The box on the bottom right-hand side shows the PagerDuty alerts that we get, which also includes the dashboard links for metrics and logs. On the Slack side, we have all the prod changes logged, so we can see what changes were happening when the alert fired. And on the dashboards, as we saw earlier, we have the ability to drill down into each of the different components. Similarly, on the logging side. And then if needed for deeper analysis, we can trigger the automation framework to run predefined checks. As an example, recently we found or encountered an issue with kubelet dbus connection. The way it manifested was we got an alert from PagerDuty saying that we were losing more number of nodes within a cluster. Based on the alert and the links, we saw that the kubelet was failing during that time. Looking through the Slack, we saw that there was an LDAP change that bounced the LDAP service that corresponded to the alert. And the kubelet log showed that there was an issue with the service connecting to the dbus. So that resulted in the nodes going not ready. As a result, we dig deeper and found that it was a bug, and we rolled out the remediation for that. A similar recent issue, we had an etcd leader churn due to connectivity issues. The churn resolved quickly, but the API server was not happy and triggered alerts for 500s. And by the time we were engaged, the API server monitor sidecar was able to pick that up and bounce the pod automatically and resolved it. Thank you for attending. If you want to participate in some of these exciting projects, Box is hiring.